Part 3 of how to get into the Minut M2 IoT device. No, AES is not broken, but every encryption algorithm has its own unique quirks that's really good to know about. In the case of AES and embedded, we're going to talk about those right now. Now, we're on an IoT device. We know that we're on an STM32F412. It's a Cortex M4 CPU. When you're on IoT devices, you're working on embedded systems. The very most modern ones might have some very advanced features, but we know that we're not on one of those. So let's go and check if we can see something interesting here. So the STM32F412, lots of RAM, good controller, can do lots of stuff. If we go further down to the F423, we can see that the STM423 includes AES encryption. We thus deduce that the STM32F412 is not using hardware-based AES encryption. It's done in software. Encryption algorithms aren't always using just the key. So to be able to use the key as a source of entropy and to put that into the algorithm, the key is most often expanded. So you have a key expansion algorithm. In AES, you are using 14 rounds when you're doing encryption or decryption with a 256-bit key. And indeed, there's a key expansion. You create new keys for every round from your original cipher key. So AES requires a separate 128-bit round key block for each round plus one more. We go and check this key schedule. To create these round keys from your original private key, you need to put them somewhere. And I know, since this CPU isn't using hardware AES encryption, that you're going to put those round keys in RAM. The quirk of AES that I was referring to in the last episode was not only that the round keys are going to go into RAM, but in AES, the round keys are as sensitive as the original private key, because you can go from the round keys to the private key, regardless of if the key has been used for decryption, what we do when we flash the original Minut apple.firmware and boot.firmware, or encrypt, which is what we want to do once we have decrypted them. If we have only 32 consecutive byte portion of the key schedule, we can go back to the private key. What I need to do now is to dump the SRAM from the M2 device at the very moment it's decrypting one of the original Minut firmware files, and then go and hunt down the portion of RAM that contains the round keys. We're thus back into SecFlash. So I've done some more decompiling here, or reverse engineering. I have figured out that we have a few buffers here of interest. And I'll show you the key struct thing. So when we're at this point in this method, before we get to decrypt, etc. down here, we clear one of the buffers. Then we perform a method that I've named getKeyStruct. It goes down into the vault, and it will return a pointer. The pointer +8 is the length of the current key that has been fetched, and we know that we want a 32-byte key, and that's what they're making sure here. And then it will enter a method I've named create AES tables with some buffer, and a keystruct +12, which is where the actual key is. So it's a pointer to the actual key, that address down in the vault. And then we enter hex 100 here, so 256, and that is actually the AES method we want. So this is AES 256. The buff we sent down from the secbuff command is passed into here, is passed into create round keys. And here, and this is also len here, is the AES 256 we selected. So you can see this is where we select the AES method, depending on the actual length, 24, 256, and 128. And this is the amount of rounds that we're going to use. So it's either 10 rounds or 12 rounds or 14 rounds in AES. And then we create these round keys and they're put into that buffer. And as you saw, that buffer comes all the way from our secflash command. So we know that this buffer, which is on the stack, if we scroll up here, that's the tables buffer, it's going to live for as long as this method is executing. It's cleared here. And then once we've created it, we're going to have a while loop that's going to do all the decryption for us. Here we have the while loop, and here we have, I have named it, this is the decryption method. You can see decryption failed, and it takes these buffers in. So during the time we are decrypting and flashing the files we're loading onto the internal flash, we know that we now have these round keys in RAM. So now we need to go and hunt that down, and they're on the stack. This is somewhat tricky. So I have a binary that I've taken from the RAM at the moment I was doing this. And with some knowledge of how the stack is working, we're now going to try to figure out where these specific structs exist. So let's move over to secflash bin. And here I am high up in the stack. And so we scroll down, and these are my comments, of course. So I assume that when I wrote this command on the command line, that was put on the stack. And we scroll down, and we can see we try to follow possible stack values here at the moment. So we can see that we have, that stack address is pointed to from some method. We could go and look up what that is about. A5 is uninitialized memory. We continue down and we can see these values. You can see here that we have a new line. We keep going, we're in the stack, and you know the stack starts off at a high value and goes down in memory range. So the more I scroll here, the newer the stuff we're seeing is. And now we get to apple.fw and secflash. Now these are two strings, so now something has handled what I wrote on the command line and made that into two different strings. We continue and we can see that we're now referencing these from the secflash, something in secflash. We can see more values, and as we're doing this, we need to figure out at which point are we getting near to the buffers we're looking at. Again, something here, secflash apple. Here's -1. I don't know what something new means. These are my comments from a few months ago. And now we get some just bytes of various values. And this is actually what we're looking for. This could be the encrypted data so we're doing decryption at the moment that we took this RAM, trying to figure out the distance between code that is using these buffers, so having allocated these buffers. So we keep going. And all of this is interesting because these are obviously encrypted data or decrypted data, or, you know, possibly the round keys. And here I set 90 bytes here until next. And when I get here, I see this value, which is 14, which is of interest, you know, because the round keys struct starts off, if we go back to the code, let me show you this because that is actually how I managed to do this. If we go down here and we go down into the create round keys, we can see that we are figuring out the length with the number of rounds. We put that into this variable, and then we set that as the first value of the round key buff. So now when I go back to our dump of the stack and I see 14 here, and I see something addressing this, I am now pretty sure that we are actually looking at the round keys. So I start here and I then check how many bytes do we have. I save that actually save more because you don't know if this value is spurious or not. Pointers to stack, I mean, that could be old code, having looked at this, and then much more newer code has run, etc. So I just save all of this down, and then I start looking at if these are the round keys, they should have some sort of relationship to one another. All right, so I take all of those bytes that I have, put them up into some structure that I can work with as they are used by AES. We check this, the number of lines I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Remember, it's 14 plus 1. And then I try to figure out, is there a relationship between them? So if I take the word 8 and I XOR that with the word 9, I should get the word 17. And I do. I have the round keys. What I now need to do is to get from the round keys to the original private key. And for that, I'm actually using pure Python AES library that I found on GitHub, and shout out. And I then go and implement a method to reverse keys. And once I have that, I am able to run this code with the round keys, and I get the Minut firmware encryption key. I can finally write some Python code that will parse the P2XF header that are in the Minut firmware files, and I can decrypt the file, the Minut application firmware file. And this is a much more interesting file than the others. Let's just see here. So I showed you before that binwalk on the actual firmware didn't show us anything. If we do binwalk on this decrypted application file, we immediately see that there's the AES S boxes and inverse S boxes, and that there's SHA-256 hash constants, and we'll get to those. And if we do binwalk on the boot firmware, which we now can decrypt from the firmware, we can here as well see that there's SHA-256 hash constants. Now we need to write another piece of software. Now we need to do the build firmware. So I can decrypt these firmware files, I can edit them, and I can then build new firmware files and flash to the device. At this point, we're actually done. We're able to extract the key that we need from the platform. We can decrypt the binaries that are running from Minut. We can change the code that's running in those binaries, and we can flash those back to the device. They'll be accepted and they'll execute. So now I want to make a proof of concept so that I can make a proper disclosure to Minut. Then I decide that there's functionality in the application where you're allowed to set some settings, but you're not allowed to set some of the other settings. Being able to set any settings I'd like would seem to be a pretty good proof of concept. So these are the commands we have available when we're running the application. And one of the commands is get. It shows us lots of properties that we can set. Some of those we are able to set as well from within this menu, and some of them we're not. So there is one property called AP hostname, and that's the property that tells the Minut device which endpoint it should speak to. So the Minut cloud service. And if I try to set that to something, I'm going to be told that the AP hostname is read-only. I'm not allowed to configure my Minut device to not use Minut Cloud, which I think is quite fair. So as a proof of concept, I now want to go and change the code so that I can set all of these and then send my images on to Minut. So after having figured out the bytes I want, I'm going to use the patching method that I built into my firmware builder. And so I'm going to go from an unmodified decrypted file, and I'm going to create a hack file. And I'm telling my script that this is the application firmware file. And so it builds. Go back in. And let's paste that command and send on my hack file. Now, we can't do secflash here actually, because when we're in application, we don't have that command available, memory limitations. So what we do is reboot, connect back during the boot, and anything we write here now will abort the regular boot process, and we're going to stay in P2 boot. So now we can do secflash, my new hack firmware, and it's going to verify my file. And once it's done, we boot. And hang on, verifying application by secboot failed to boot. Command exited with status -7. Ah, yes, secboot. This is actually the 7 here. 7 and 8 are different return values that the secboot command can return when it's verifying an application. It is actually this code that we looked at before that compares 32 bytes. That's an SHA-256 HMAC done over the decrypted part of the firmware file. And I'm not going to go into details on this. We're done with the exploit. I'm going to explain what I did for my proof of concept. I will make a 4th video where I go through in detail some of the other things that I found regarding Minut's architecture and firmware. But for now, let's go to the closing comments. I couldn't find a security contact on Minut's website. I went on LinkedIn. I know, sometimes you have to. I looked up and I found the head of hardware and co-founder. I guessed at the likely corporate email setup and sent an email. 13 minutes later, I had a reply. 2 days after, they had gone through my security report in detail. And about 2.5 weeks after disclosure, they had already sent out new firmware. I don't know actually how it comes across when you do a video like this, that I'm breaking through the security and I'm using some of the horrible words like pwn and I've defeated it, etc. This is by far the best architectured from a security standpoint IoT device I've ever seen. While reading out the RAM is an issue, if you saw, basically ST Microelectronics are saying that RDP1 is as secure as RDP2. I wonder how many devices out there on the market are in RDP1 when they shouldn't. Round keys in RAM, being able to calculate those back into the private key. Minut hasn't rolled their own AES. They're using a third-party library. I'm not naming it because I've actually sent not a security advisory, but a reminder that maybe this is something they would want to communicate. They're well known. They're considered to be very secure. There'll be a 4th episode. I'll go through some of the other things, network communication, settings. You might want to stick around for that episode as well, but if you decide that you're going to end it here, thank you so much for watching. I hope this was fun. I hope that there was something new here for the beginner as well as for the expert. I don't know how many other red teaming videos I'll be able to make. I'm very happy and grateful to Minut for the whole disclosure process, where they kept me constantly updated with what they had done. I know that I have no idea at the moment how I would break into the updated firmware on the M2. What I will say though is that there will be an episode regarding fault injection, voltage glitching to come, and I'm actually gonna use the Minut M2 as my test device. One of the things that they knew about their M2 device was that the STM32F4 series is glitchable. And so I took on that challenge and, checked myself to see if that really was a good way to get into that device. Until then, cheers.